This is your presenter Asloob Mudassar, and I am presenting slide number 27 of the course on laser physics. The question is, using semi-classical approach, calculate the electric dipole moment of a two-level atom. Answer. Classically, an atom can take any amount of energy. That is, the energy levels are so narrowly spaced that there is a continuum of energy levels. Semi-classical approach assumes discrete levels in an atom, each of which has quantized energy. Let us consider an atom with two non-degenerate energy levels with energies E1 and E2. The wave functions corresponding to the two states can be written as psi1 as a function of r and t is equal to u1 of r into e to the power minus iota e1 over h bar into t. This is equation number 27.1. And psi2 of rt is equal to u2 of r into e to the power minus iota into e2 over h bar multiplied by t. This is equation number 2. u1 of r and u2 of r are eigenfunctions of the stationary states of the level 1 and 2 respectively. R is the position of the electron as measured from the nucleus center. The eigenstate of the atom is given by the superposition of the two eigenstates and is given by. So the eigenstate of the atom is given in equation number 3, which is the superposition of two states. So psi of rt is equal to a1 of t into psi1 of rt plus a2 of t into psi2 of rt, where a1 of t mod square and a2 of t mod square give the probabilities of existence of the atom in state 1 and state 2 respectively, and can be written as a1 of t mod square plus a2 of mod square is equal to 1, because the total probability of existence of the electron in these two states is 1. E into psi mod square may be considered as an elemental charge per unit volume at the position r and at the position r from the nucleus. The elemental dipole moment due to this charge is d mu is equal to minus the charge in the element dv, which is E into psi mod square into dv multiplied by the position r, which can be written as mu is equal to minus integral of E into psi mod square into r into dv, as given in equation number 27.5. So this is the total dipole moment of the atom, where psi mod square is given, can be written as psi into psi star, where psi star is the complex conjugate of psi, and substituting the values of psi and psi star from equation number 27.3, plug in these values over here, and then multiplying and expanding the two parentheses, we get the second expression in the equation. And then you know that we are introducing the values of psi1 and psi2 from the previous equation, that's from equation number 27.1 and 27.2. Substituting these values, we can have the term e to the power iota e2 minus e1 over h bar into t. So this term will appear, and also its conjugate, that is e to the power minus iota into e2 minus e1 over h bar into 2. These two terms appear when we substitute the values of psi1 and psi2 in terms of their expansions. Now we can rearrange the term, and we get the last expression, which is a mod square into u1 mod square plus a2 mod square into u2 mod square plus 2 into the real part of a1 a2 star u1 and u2 star into e to the power iota omega naught t, where omega naught is equal to 2 pi nu naught, and that is equal to e2 minus e1 over h bar. And nu naught is the transition frequency when the atom decays from level 2 to level 1. The dipole moment of the atom mu can now be written as. So what we are doing, we are substituting the value of psi mod square given in the end expression, the last expression of equation number 6 into equation number 5. We get this equation, that is equation number 7. So we have these three terms, and we have expanded the integral over the three terms. And then you know that in the third expression we have introduced mu to 1, and then in the fourth expression we have introduced mu OSC, that is oscillation, where mu oscillation OSC is given by the real part of 2 into A1 into A2 star into mu of 2 1 e to the power iota omega naught t, as given in equation number 8. Now we explain these terms. So mu OSC is the dipole moment of the atom oscillating at omega naught. So you see that the dipole moment of the atom will oscillate at a frequency omega naught, as evident from the expression given in equation 8, and is associated with the transition from level 2 to level 1 with the magnitude proportional to. And you know that the equation 8 contains mu to 1, where mu to 1 is the magnitude of this dipole moment, and given in equation number 9, that is mu to 1 is equal to the integral of E into mu 2 star mu 1 into R into dV. This can be found from the third last and the second expression of the equation number 7, where we introduced mu to 1, for example over here. So we have written the dipole moment of the atom which is oscillating at a frequency omega naught, and we have also written the magnitude of this dipole moment as given in equation number 9. These two terms, the first two terms in this dipole moment, you see that these are the constant terms, and it means that the first two terms in equation number 7 are independent of time. The first two terms on the right hand side of equation number 27.7 are independent of time and have a fixed contribution to the atomic dipole moment, and the variation in the atomic dipole moment is mainly contributed by the third term, which makes a significant contribution. The atomic dipole moment is thus written as mu is approximately equal to mu oscillation, because we are writing approximate sign because we are only considering the third term, ignoring the constant contributions from the first two terms. So the atomic dipole moment of the atom is mu is approximately equal to mu oscillation is equal to 2 into the real part of A1 A2 star mu to 1 into e to the power iota omega naught t. And here we are separating the magnitude of this quantity, which we have written in the form of a modulus in the real part on the right hand side, which is mod of A1 A2 star into mu to 1, and then we have multiplied by the term into e to the power iota 5. That is, we have written this complex quantity into the magnitude of a complex quantity multiplied by its phase value. So we have written the last expression in the first row is equal to 2 into the real part of mod of A1 A2 star mu to 1 multiplied by its phase value, which is equal to e to the power iota 5, and then we have the term e to the power iota omega naught t. So you see that then we can take the magnitude part out of the real sign, that is 2 into the mod of A1 A2 star mu to 1 multiplied by the cos of omega naught t plus 5, because we can add two exponential terms because we have e to the power iota, within the bracket we have omega naught t plus 5, and we can, since we are considering the real part of that one, which is equal to cos of omega naught t plus 5. So we have simply written the last expression as the atomic dipole moment of the atom mu is equal to mu naught into cos of omega naught t plus 5. The atomic dipole moment oscillates sinusoidally with amplitude mu naught mod is equal to 2 into the mod of A1 into A2 star multiplied by mu to 1. So you see that in equation number 27 we have calculated the atomic dipole moment of the atom using a semi-classical approach, and the magnitude of that dipole moment is given in as mu naught, as absolute value of mu naught is equal to 2 into the mod of A1 A2 star into mu to 1. So this completes our answer. So this is the end of slide number 27.